Hey everyone, today we're going to kick off the first lesson of Unit 3. So we have covered in Unit 1, we've covered limits and continuity. In Unit 2, we introduced the idea of the derivative, the slope of the tangent line, and then we talked about some basic rules like the power rule, the quotient rule, the product rule, sum and difference rule, constant multiple rule, constant rule. We talked about all those shortcuts essentially to taking derivatives. And then we introduced the idea of particle motion and how calculus applies to movement. So we talked about speed and velocity and acceleration and position and how all those are tied together. This unit primarily focuses on more and more derivatives, more higher end derivatives, which means we're going to be focusing on trig functions and how to take derivatives of trig functions. We're going to be talking about exponential functions and logarithmic functions. We're going to be talking about composition of functions and inverse functions, just a whole slew of different types of functions that we can take derivatives of. And our goal by the end of this entire unit is to be able to take the derivative of any function out there, essentially. So with that said, let's go ahead and jump in. Before we go into some basic trig functions, and to be honest with you, you already know two of them, but we're going to rehash those in a little bit. Before we do that, I wanted to talk a little bit more about the relationship between velocity and acceleration and position and all of that. So with that said, I kind of summarized all of these concepts that we talked about last unit in this one slide, okay? First of all, movement. How do I know if I'm moving to the right? So how do I know I'm heading in the positive direction, essentially, if we define right to be the positive direction? We know that we are moving to the right when velocity is positive, okay? In other words, our position function, if you were to look at a position function, it would be increasing. If my position is increasing, that means I'm moving to the right, and therefore my velocity will be positive. So we'd say v of t is greater than 0. In the same way, how do I know when I'm moving to the left? I'm moving to the left when velocity is negative. And on a position time graph, you would see that function decreasing. We're moving to the left. So we'd say v of t is less than 0. Okay. How do I know I'm moving away from the origin? Now, this is not something that we directly talked about in previous lessons, but this is a very good thing to understand, a very good thing to relate two different levels of functions. How do I know I'm moving away from the origin? Well, the truth is that depends on which side of the origin you're on. So if this is my origin and I'm moving back and forth along this number line, how do I know that I'm moving away from the origin? Well, if I'm standing on this side of the origin, how do I move away? I have to move to the left. And if I'm standing on this side of the origin, then to move away from the origin, I have to move to the right. So the first question we have to ask ourselves is, where are we at? Which side of the origin are we on? Well, how do we tell which side of the origin we're on? We have to determine the sign of the position function, okay? So looking at the position function of x, we have to ask ourselves whether x of t is positive or whether x of t is negative, right? So if x of t is positive, I guess I should have flipped those around. If x of t is negative versus x of t being positive, okay? Now, how would I move away from the origin if my position is negative? Well, I would have to move in that direction. I'd have to move to the left. Well, how do I move to the left? Like I just said in the previous statement, I move to the left when velocity is negative, right? So I'm moving away from the origin if my position is negative and my velocity is negative. Going over here, if my position is positive, how do I move away from the origin? Well, my velocity would have to be positive. That would mean that I'm moving to the right. Okay? So these are the two cases where I could be moving away from the origin looking at simple one-dimensional direction. Okay? Essentially, we can summarize it this way. We can say that we are moving away from the origin when position and velocity have the same sign. Okay? So we are moving away from the origin when position and velocity are either both negative or both positive. And so we can kind of extrapolate from that. How do I know I'm moving toward the origin? Well, same type of question. I'm moving toward the origin depending on which side of the origin I'm on. So if I'm on this side, right, how would I move towards the origin? I would have to move to the right. But if I'm on this side, I would have to move to the left. And so if my position is negative, my velocity would have to be positive, okay, to move toward the origin. Or if my position was positive, then my velocity would have to be negative to move toward the origin, okay? So we can summarize it that way. And I guess it would be a good idea to have these number lines written down so that you can see if I'm on this side, oops, for this case, moving away. If I'm on the left-hand side, I have to move to the left. If I'm on the right-hand side, I have to move to the right. And then down here, moving toward the origin. If I'm on the left-hand side, I have to move to the right. And if I'm on the right-hand side, I have to move to the left. So we can summarize it this way. Moving toward the origin, when x of t and v of t have opposite signs. Okay, so those are the two scenarios here. We're either moving away from the origin or toward the origin, or we're not moving at all. I kind of summarize that really quickly here. It's when position is positive and velocity is positive, or when position is negative and velocity is negative. But I think writing it out in the sentence and seeing the picture really helps us understand that relationship. It's a relationship between position and velocity, okay? Same thing for moving toward the origin. That would imply that the position is positive and velocity is negative, or position is negative, velocity is positive. In other words, opposite signs, okay? Now let's talk about the velocity function and the speed function, okay? Velocity, remember, is the rate at which the position changes. How do I know when velocity is increasing? Well, velocity is increasing when acceleration is, let's do this, let me get rid of this, when acceleration is positive. And why is that? Well, if you think of the chart, and we will be more and more exposed to this chart as time goes on, okay? We have three different functions, and they all interrelate. If position is positive, that implies velocity is, if position is positive, that doesn't imply anything for velocity. Same thing if position is negative. That just tells us which side of the origin we're on. If position is increasing, that implies velocity is going to be positive. And if position is decreasing, that implies velocity is going to be negative. So we have this relationship here, and we've seen that in a graph. If I'm looking at a position graph and I see it going uphill, that implies that the velocity is positive because position is increasing. The slope is positive. But we can go down to the next level and say, okay, well, if velocity is increasing, that would imply that acceleration would be positive. And if velocity is decreasing, that would imply that acceleration is negative. Why is that? Because velocity is the first derivative of position. So this relationship holds true between a function and its derivative. Well, acceleration is the first derivative of velocity, which means that it holds the same relationship. See that? These two are related because this is the derivative of this. These two are related because this is the derivative of this. So how do I know when my velocity is increasing? My velocity is increasing when my acceleration is positive, okay? And then opposite, the velocity is decreasing when the acceleration is negative. And so we have that relationship there, okay? Now, here is the one that I really emphasized the other day. How do I know I'm speeding up? Well, speeding up is knowing whether I'm speeding up or slowing down, or another way of saying that, how do I know when my speed is increasing or decreasing? That is a relationship between our velocity and acceleration. Okay? So just a second ago we talked about whether I'm moving away from the origin or toward the origin, and we showed that it's a relationship between these two things. If position and velocity have the same sign, that means we're moving away from the origin. And if position and velocity have opposite signs, that means I'm moving toward the origin. Well, when I'm talking about speeding up and slowing down, it's going to be the same type of relationship between these two guys, the velocity and the acceleration. Okay? So I think this is better. It is better to picture this rather than graph it out. I'm speeding up if I am moving in a direction and something pushes me to move faster in that direction. Okay? So I'm moving in a direction that is based on velocity. My direction is based on my velocity. So if my velocity is positive, then how do I speed up? It would be if acceleration, the force behind the velocity, propels me, pushes me. Okay? Whereas if acceleration was being opposite to me, so if my velocity is positive and my acceleration is negative, then it's pushing against me, and so eventually I'm going to come to a stop, or I'm going to slow down as time goes on. So the bottom line is I'm speeding up if velocity and acceleration have the same signs, and I'm slowing down if velocity and acceleration have opposite signs. Okay? So I'll go the other way, and I kind of already explained this in a previous video, but I want to emphasize it because it's important. If my velocity is negative, that means I'm traveling that way. If I have a force on me that is going in the same direction, that means I'm going to speed up. So if my velocity is negative and my acceleration is negative, I'm going to speed up. Whereas if my velocity is negative, so I'm moving that way, but I have this force that's fighting against me, that acceleration is fighting against me, I'm going to slow down. Okay? So again, I'm speeding up when velocity and acceleration have the same signs, and I'm slowing down when velocity and acceleration have different signs. Okay? So these are just some very important relationships in the position context of calculus. It's something that you're going to want to not just memorize, but really understand. And in my mind, I picture all of this stuff. I don't have it necessarily memorized. I picture myself moving in one direction or another. I picture myself where I'm at on a number line, whether I'm on the positive side or the negative side, and I envision these things rather than just memorize them, because I want to understand why these things are happening. Okay? So let's go ahead and take a look at some trig functions. So far, we've only really dealt with polynomial functions when it comes to taking derivatives. But now let's get into some trig functions. Now we already know that the derivative of sine of x is equal to, dun dun dun, cosine of x. Now I'm not going to spend the time proving that today. We did an experiment. We graphed out sine and we plotted some points for the slope function and for the derivative function in a prior lesson, and we discovered that it is cosine of x. To prove this, we would have to have a very good understanding of our trig identities, which is fine, but I'm not going to do that in this video. I'll go ahead and do that in a separate video. Okay? So we know that the derivative of sine of x is equal to cosine of x. And in fact, we already know that the derivative of cosine x from a prior experiment is going to be negative sine of x. And so I'll go ahead and do that here just to emphasize that. If I'm looking at the cosine graph, cosine looks something like this, where this is 2 pi, and then this is pi over 2, this is 3 pi over 2. Okay? If I want to graph the derivative, so we'll call this y prime, and again, this is cosine of x. Okay? If I want to graph the derivative, again, the first thing I look for is where we have a zero slope or a horizontal tangent line. Here we would have a horizontal tangent line because cosine keeps going the other way, so it's not really an endpoint. Here we have a horizontal tangent line, and here. So that means at 0, the derivative is 0. At pi, the derivative is 0. And at 2 pi, the derivative is 0. Okay? From there, I look for where the function is increasing. Well, the function is increasing from pi to 2 pi. If the function is increasing, that implies that the derivative is positive, okay? And then where the function is decreasing, well, when a function is decreasing, that would imply that the derivative is negative. So I know that the values that my derivative holds must be within these regions, or within these regions it must be negative and positive. The last question I ask is where the graph is the steepest. Now in trig functions, especially cosine and sine, the steepest is right in that middle there from 0 to pi. Pi over 2 is the steepest point. If I were to draw a tangent line there, that would be steeper than any other tangent line in that interval. So from 0 to pi, the steepest point implies on the derivative the lowest point. Okay? Same thing here, the steepest point, the steepest part of the graph here is going to be at 3 pi over 2. That would imply the highest point on the derivative graph. And so we can kind of see that we start off with the slope of 0, and then we get less and less and less and less until we get to the least point, and then it starts climbing back up again, back to 0. So it kind of bounces back like that. And then over here, it's 0, and then it gets steeper and steeper and steeper, which implies this is getting bigger and bigger and bigger. Since that's the steepest, that's the highest it'll get. And then it starts to shallow out again, which means the slope starts approaching 0 again. And so we have this graph on this side. And so we can easily see that this is just the reflection of sine. So if y equals cosine of x, that would imply that y prime is negative sine of x. Okay? So that is that guy. And I just kind of went through this process that I'm describing on the lesson here on the board. So we know that if the function is cosine of x, the derivative is negative sine of x. All right? Now, with that said, let's see what else I have here. I do want to add something. Let's go ahead and look at something else real fast. Let's talk about higher order derivatives. First of all, we know that if y equals sine of x, well, let me rewrite it a different way using Leibniz form. If I want the derivative of sine of x, we know that that is cosine of x. And the derivative of cosine of x is negative sine of x. We just kind of explored that right now. Now, let's keep going with this. What is the derivative? What is the derivative then of negative sine of x? Well, that should be pretty easy. The negative is just a coefficient. It's just a constant multiple. So this would be the same as saying, let's take the negative 1 out and then multiply that by the derivative of sine of x. And since the derivative of sine of x is cosine of x, we'll multiply it by negative 1 and we get negative cosine of x. Okay? And then we can keep going with that. Let's find the derivative of this guy. So the derivative of negative cosine of x, we'll do the same thing. Take the negative 1 out, oops, and then take the derivative of the cosine of x. The derivative of cosine of x, well, so we'd have negative 1 times the derivative of cosine of x, which is negative sine of x, which simplifies to sine of x. And then we're back to square one. So the derivative of sine is cosine, the derivative of cosine is negative sine, the derivative of negative sine is negative cosine, the derivative of negative cosine is sine. So it's a cycle, it's a cyclic thing, and that kind of makes sense because we're talking about trig functions, and trig functions cycle back and forth. I had a student a few years ago come up with this little pattern or this little note that they would write down so they wouldn't forget it. If I'm talking about sine of x, the derivative of sine of x is cosine of x. The derivative of cosine of x is negative sine of x, and the derivative of negative sine of x is negative cosine of x. And therefore, the derivative of negative cosine of x is back to sine of x. So it's kind of cool that it goes in a circle like that. Okay? And this is going to help us actually when we get to something called antiderivatives or integrals, because we're going to go backwards. So if I said, what's the antiderivative of cosine of x? It would be sine of x because we're going backwards. So that's why I always put the arrows there to help me see it. So that really helps me out here. So if I were to say, let y equal the sine of x, what is the fifth derivative? And the way I could write the fifth derivative is this. That's like the fifth derivative. What's the fifth derivative? Well, first derivative, second derivative, third derivative, fourth derivative, fifth derivative. So the fifth derivative of sine of x is cosine of x. Yeah, so something along that line. Now, it'd be interesting to say what is the I don't know, the 138th derivative of sine of x. That's gross. But the fourth derivative, every multiple of 4 gets us back home. So I'm going to divide this by 4, and so I end up with, what is that? That's going to be 30, 18, 34, and with a remainder of 2, essentially. So basically, 138th derivative, that means I'm going to go around this thing 34 times to get back here, and then I have to go 2 more to get to the answer. So that would be negative sine of x. So anyways, I thought that's an interesting idea. All right, let's go ahead and take a look at an example of applying this. I want df dx if f of x is equal to x to the third cosine of x. X to the third cosine of x. And I am looking for df dx, which just means I'm looking for the derivative. All right. What do we recognize here? Well, I can tell you right now, I'm sure I'm going to get some students that are going to take the derivative wrong. They go, oh, I know the derivative of x to the third, that's 3x squared. And good for you, you're right. I know the derivative of cosine of x, that's negative sine of x. And so therefore you simplify it and you call it done. But I have warned you in previous videos, and it's very important that you recognize this. Do you see multiplication? The answer is yes, we see multiplication right here. Then we have the product rule. We can apply the product rule, okay? We do not want to screw that up. Product rule, for whatever reason, always gets forgotten. Product rule, because we are multiplying. Would the product rule produce this as a derivative? No, absolutely not. So let's use the product rule. Remember, the product rule said the derivative of the first thing, so 3x squared, times the second thing, so times cosine of x, plus the derivative of the second thing, which is negative sine of x, times the first thing, x cubed. Now, what I don't like about the way I wrote this is right here, sine of x times x cubed. Am I multiplying to x and x cubed? No, so I should put this in parentheses. Anytime you have an argument of a trig function, it should be in parentheses. But this can be simplified a little bit to say 3x squared times cosine of x minus x cubed times sine of x. So that would be my derivative of that function. And if you wanted to, you could factor out x squared if you find that beneficial for some application. And we'll get more into that kind of stuff later on. But that is an example of taking the derivative, using trig functions, and applying the product rule. Okay, so we are correct there. Let's go ahead and look at a little bit more in depth of a problem. We've got x of t equals cosine of t, and so this is going to be a particle motion problem. X of t equals cosine of t. Okay, and it says, so that's the position. What is the velocity and acceleration when t equals pi over 6? So what I would like you to do is pause the video, see if you can answer these 3 questions on your own, and if once you get stuck or once you think you have your answers, push play and see what you come up with. So for number 1, it's asking for the velocity and the acceleration at a very specific point in time. And then it says which direction is it moving and is it speeding up or slowing down. Okay, so what I have to do first is take the derivative so I can get my velocity. So I would say the velocity is equal to the derivative of position. That's always a good thing to state. And therefore, that would be negative sine of t. Okay? Then we can say my acceleration is the derivative of velocity. And since the derivative of velocity is negative sine of t, we end up with cosine of t. No, sorry, negative cosine of t. Just went through that circular motion and then I forgot about it. So there I've got my velocity and acceleration functions, and I'm looking for the velocity and acceleration at pi over 6. So v of pi over 6 is negative sine of pi over 6. Well, sine of pi over 6, that's going to be, what is that going to be? That's going to be 1/2, I believe, so negative 1/2. Okay. And then we will figure out the acceleration at pi over 6, which would be negative cosine of pi over 6. And the cosine of pi over 6 is going to be rad 3 over 2, so that would be negative rad 3 over 2. And so we can see that we have our velocity and our acceleration. Great, those are the two answers that it asked for, but it also asked another question. Okay? It said, is the particle or is the object speeding up or slowing down? Well, this is why I visualize it. My velocity is negative, so that means I'm heading that way. And then I have a force on me that is negative, so that means it's pushing me that way. Since those agree, it's going to be that I'm speeding up. So I would say speeding up, or my speed is increasing, since v of pi over 6 and a of pi over 6 have the same signs, Now, I don't like saying, as some students might say, well, because they're both negative. That's true, but that might cause confusion in other contexts. Like if somebody was to read your justification and you say velocity and acceleration are both negative, if somebody were to read that and then try to apply what you said to another problem, and they ended up with both being positive, they might not recognize that that is also speeding up. So this is more of a general statement that is true on every context. So speeding up because velocity and acceleration have the same sign. All right, let's make sure I am right before I move on to the next thing. I am, so that's perfect. Okay. Oh, and it said, oh, I forgot to answer, which direction is it moving? It is moving to the left because velocity is negative. Justification matters, okay? So we're moving to the left because velocity is negative. Let's go ahead and take a look at number 2. Number 2 is not so much an application as it is just practice. We've got f of x equals cosine of x over x. And we are looking for f prime, f double prime, and the equation of the tangent line of f at x equals 2. So let's just go ahead and find f prime. Well, how do I take the derivative of that guy? Well, that is a quotient, so we're going to use the quotient rule. Remember, the quotient rule says the derivative of the top thing, which is negative sine of x, times the bottom thing, so times x, I'm going to put parentheses around the argument, minus the derivative of the bottom thing, the derivative of x is just 1, and then times the top, so times cosine of x, all over x squared. And I'm going to simplify this a little bit. F prime of x, we'll say negative sine of x, negative x times sine of x, minus cosine of x, all over x squared. Now, it also asked for f double prime. Well, that would be the second derivative of f, so we got to take the derivative of this guy, and that honestly looks like it's going to be disgusting, but we're going to do it anyways. So again, it's going to be quotient rule here. So we want to figure out the derivative of the top. Well, to figure out the derivative of the top, I have a product here. So this is good practice in applying different rules of derivatives when we have multiple things going on at once. So I'm going to do this. I'm going to say that if, remember how do I want to say this? If I want the derivative in respect to x of u over v, where both of these are functions, it's u prime times v minus v prime times u all over v squared. So I have to figure out the derivative of the top thing. Well, the first thing I want to do is identify what the top thing is. The top thing is all of this up here. So I got to take the derivative of that. So I'll call that u. What is u prime? Well, I'm going to use the product rule for this piece, and then I got a sum and difference there, so that's pretty easy. The derivative of the first thing is going to be negative 1 times sine of x plus the derivative of the second thing, which is cosine of x, times the first thing, so times negative x. So that's just the derivative of this piece of the top. Then I have to figure out the derivative of negative cosine of x. The derivative of negative cosine of x is positive sine of x. So that's the derivative of the top. All right? Yeah, that's the derivative of the top. And then we have to multiply it by the bottom and everything else. So we'd end up with negative sine of x plus cosine of x. Oops, I missed something there. Oh, you know what? We can simplify this. Let's simplify this. You got a negative sine of x and a positive sine of x. Those cancel out. So you're left with negative x times cosine of x for the top, negative x times cosine of x. That is just the derivative of the top piece. Then times the bottom piece, so times x squared, minus the derivative of the bottom thing, which is 2x, times the top, so I'm going to put this all in parentheses, times negative x times sine of x minus cosine of x. Oh no, I'm running out of room. So that's derivative of the top times the bottom minus the derivative of the bottom times the top all over the bottom squared, which would be x to the fourth. Okay. Can I simplify that any more? Maybe a little bit, so let's go ahead and do that so we can see it clearly. X times x squared is negative x cubed times cosine of x. And then here, I've got maybe some distribution to do, so I'm going to get plus 2x squared times sine of x plus 2x times cosine of x. So I distributed that negative 2x all over x to the fourth. Whew, boy, this is a lot. Now, we can see that this term, and this term all have a common factor of x. So let's just divide the top and the bottom by x. We'd end up with negative x squared times cosine of x plus 2x times sine of x plus 2 times cosine of x all over x cubed, because we factored out that common x. All right, I really hope I'm good with that. But that would be the second derivative. You can see how complex these derivatives can get. The last part of number 2, it said find the equation of the tangent line of f at x equals 2. So remember, to find the tangent line, you need two things. You need your point. Well, how do I find the point? The point was when x equals 2, so we have to plug that back in up here. So it would be f of 2 equals cosine of 2 over 2. That can't be simplified too much, but that's my point. And then I need to find my slope, and I find my slope by figuring out what f prime of 2 is. So that would be negative 2 times sine of 2 minus cosine of 2 all over 2 squared. And so I'm not going to simplify all this. My tangent line is going to be y minus cosine of 2 over 2 equals, my slope is all of this, and this is all a numeric value because there's no variables in it, so we can just write it like this actually, all over 4, and then times x minus 2. So that is my tangent line. Yeah, that looks gross. We could type it in our calculator and get a numeric values for those things, but I don't know if it's necessary. Let's make sure I am right here. We got the derivative right, so that's good. And I guess I didn't do anything else, so we're not going to know whether I did that right or not. That'll be up to you to decide if I did that right. Hopefully I did, and then obviously the tangent line as well. All right, let's go ahead and take a look at number 3. More practice. We've got g of x equals 2x sine of x. I'll put parentheses around that. Cosine of x. Interesting, cosine of x. Ooh, I like this. This is really diving into different rules of derivatives. And it's asking for us to figure out what g prime of x is. That's our goal. Now, the first thing I need to recognize is that I have two products here. Okay, so I'm going to go ahead and put multiplication signs in between those. Those are two products. And we're going to have to use the product rule twice to be able to do this effectively. Well, let me go ahead. It's going to be interesting here. I'm going to call this u, and I'm going to call this v. Okay. Now, you could have broken this down any way you wanted to. You could have called 2xu and then all of this v if you wanted to. But I'm going to break it down like this. And so if I want the derivative, oops, wrong marker. If I want the derivative of g, that's going to be equal to u prime v plus v prime u. Right? That's the product rule. Well, to figure out what u prime is, I've got to figure out the derivative of this, which is another product rule. Okay? So I would say this. I'm going to write it this way. I'm going to say u prime equals, u prime equals 2 times sine of x plus cosine of x times 2x. Okay, so I use the product rule. Derivative of the first times the second plus derivative of the second times the first. So that's just u prime. Okay? Then I need v. V is right there. I need v prime, so I need to take the derivative of that guy. So v prime is going to be negative sine of x. And then I have u already listed there. So we've got a lot going on there. Now we can just plug in what we know. So it might be easier when you have multiple rules to identify parts within the main rule. The main rule here is the product rule, but then we have a sub-rule of the product rule again. So this would be 2 times sine of x plus, and I'm going to simplify that guy to be 2x times cosine of x. So that is my u prime, then times v. So I'm going to put this in brackets, times v. So v was cosine of x, plus v prime. V prime was negative sine of x, times u. And u was 2x times sine of x. Okay. Now we can simplify this probably a little bit here. I'm going to go ahead and distribute this cosine into these. We get 2 times sine of x times cosine of x, just distributing that in. And then when I distribute that in, I end up with 2x times cosine squared x, right? Because I got a cosine x times a cosine x. That's kind of cool. And then over here, I'm going to move that 2x out front, so it'll be minus 2x, and then times sine squared of x. Oh, that's a very interesting relationship there. And my guess is we could use some trig identities or trig rules to simplify that further, because I got something going on with cosine squared and sine squared. I've got something going on with sine and cosine with a 2 there. So I'm sure this can be simplified further, but I am not going to spend the time doing that. Let me just make sure I'm right, though. So 2 sine of x, 2 sine of x. Oh, I got this one. 2 sine of x plus 2x cosine of x times cosine of x minus sine of x times 2x sine of x. Here's the cool thing about like the AP exam. Are you guys ready for this? And I think I've said this before. There's no need to simplify anything if it's not asking for further answers. So if it just says find the derivative, I could have left it right here on this one, okay? Now obviously if it says find the derivative at a point, I'd have to go further with it somehow. But there's no need to simplify anything unless it specifically says so. All right, oh, I did simplify it a little bit, and it looks like I simplified it exactly how I have it here, so I did that right. All right, let's go ahead and look at the last slide here, and this one's really important, so please do not stop the video and say, oh, we're done, because really the only new thing that we learned today was that the derivative of cosine equals negative sine, and we kind of already knew that anyways. Here, we want to look at y equals tangent of x. Well, we know the derivative of sine, we know the derivative of cosine, so it just makes sense that we're going to be looking at the derivative of tangent next. So what is the derivative of this thing? I don't know. I don't know. So I can't just take the derivative because I don't know it. How could I rewrite this into a form that I know something about the derivative? Well, one really important trig identity is that tangent of x is equal to sine of x over the cosine of x. That, along with the sine squared plus cosine squared equals 1, those are the two most important ones. Out of those two, pretty much everything can be derived, okay? So we are going to rewrite tangent of x to be sine of x over cosine of x. Then from here, I can find that derivative really easily by using the quotient rule. So the derivative in respect to x is quotient rule, the derivative of the top, which is cosine of x, times the bottom, cosine of x, minus the derivative of the bottom, so minus negative sine of x. I should probably put these in parentheses here so we can see it broken apart. And then times the top, which is sine of x. and then all over the bottom squared. Okay? Again, derivative of the top, cosine, times the bottom, cosine, minus the derivative of the bottom, which is negative sine, so I got a double negative there, and then times the top, sine, all over the bottom squared. Now, you would say, Mr. Bunye, didn't you just tell me I don't have to simplify anything if it doesn't say? Yeah, except for I'm looking for something here. This one's really cool. Let's keep going with this. What's cosine of x times cosine of x? Well, that's cosine of x squared. And then minus a negative, that would be plus sine of x squared, all over, and I could rewrite cosine of x squared as cosine squared x like that. Okay. Now here's the problem. Some students are going to go, oh look, cosine squared over cosine squared will reduce. You can't do that. There's a plus sign there. That's silly. But cosine squared plus sine squared, you should recognize as 1. Oh. So that's simplified pretty nicely. And we can go one step further because we know the reciprocal function of cosine is secant. So we can then say dy dx equals secant squared x. And so now we know the three basic trig functions derivatives. The derivative of sine is cosine. The derivative of cosine is negative sine, and the derivative of tangent is secant squared x. So those are the first three trig functions you learned way back in Math 2 or geometry, and these are the three first derivatives that we learn, and we are going to build off of that because our next step is going to be, okay, find the derivative of secant, find the derivative of cosecant, and find the derivative of cotangent. From these, we can derive these by rewriting them like this. And so that wraps up the lesson for today. We will get more into this in a future lesson. I hope that you have a good feel for how trig functions work with derivatives, and then again, more particle motion and understanding that. So with that said, if you have any questions, please comment below. And I'm going to say it probably for the first time, hey, like and subscribe. Help me out a little bit. Otherwise, I will talk to you guys all later.